right. Good Monday. Let's get started. Bless you. Let's kick it off with questions. Any type of questions? No questions?
Oh.
Yes.
For the homework, can we basically just provide pseudocode for the parser?
Yes, your parser should be coded similarly to how we did in class. Right?
So is it fine if we use like Python style things like we did for in? Okay.
Yes. That would be okay. Should probably have a comment at the top that says what you're doing. That way, whoever grades it knows what's going on. Cool. Any other questions? Yes. Mm-hmm.
What do we do when we have another little a that falls? Does that homework with like little a, little a?
So,
Put that in the if statement, like after we try to see.
let's think about it. So let's say we have A goes to little a, C, A, something like that? Cool. So walk me through. What am I doing?
So you type equals
Get token.
yeah, and then you check it, you type this little a.
So why are we checking this?
See if you're doing the readable breaks or multiples, right?
Cool. Okay. Checking to make sure we're doing the right rule. We're testing the first of ACA, right? The first of this rule. Perfect. Okay. So then what?
You just do little a so you don't turn it tokens if you parse C.
Cool. So we call parse C. So assuming this returns correctly, what do we know?
Well, at that point I checked for another little a. If I did not get another little a, I did a sentence.
Yeah, so think about the input string, right? So we first read in an A, so it had to have been an A to get there.
Yeah.
And then, I don't know, then what happened? Yeah, parse C, parsed whatever this is as a C, right? So what do we know must come after this C?
Small a?
Gotta be a little a, exactly. So how can we check? And then when we return, when parse A returns, what do we want to be true? Right, so we parsed up to here, and then we called parse C, so we parsed up to here. So after A returns, where do we want to have parsed?
Get token and compare it with A.
Yeah, but where do I want to have been parsed? Do I want to return it like this? No, I want to return it as parsed all this thing, right? So that whoever called us says, hey, great, they just called parse A. All this stuff is an A. And then they can start parsing. So, like I think as both of you said, right? I'd want to get a token. And then what do I want to check?
Why check to see if the rule, if the token is little a?
If it is A, then what?
Print ACA.
Yeah. Then print the rule A goes to little a, C, A. Is that it? Am I done?
Else syntax.
Yeah, so why do I need the else? Yeah, if it's not an A here, then you know for a fact, because you've already successfully parsed a C, so the next thing better be an A, right? That's what the rule says. Parse an A, then parse a C, then parse an A. Right? So if we've parsed a C and the next thing is not an A, then this is a syntax error and this string did not come from this grammar. Yeah?
So why do we have a print after the parsing? It's kind of building the tree in the reverse fashion, bottom of fashion, and it's kind of not like the same parsing.
So could we print, let's say here? So it's kind of a theoretical, I mean, it's more of a philosophical question. So could we print here?
We can print it here.
Yeah, so we've decided between all the different rules of A, right? By looking at that first token, we've decided is it A goes to ACA or is it A goes to beta or gamma or delta, whatever, right? We've decided it's A goes to little a, C, A. But what do we actually know that we successfully have parsed an ACA?
But if there is an error, it will come in C, parse C.
Right, it'll come in parse C, but we said the rule A goes to little c, little a, big C, A, when really that's not true because it's an invalid parsing. So it's really just a matter of, it's more preference. To me it makes sense at the end because here, right here is when I know that this is a valid rule. Up until this point, all along here, it could blow up, right? It could not be a C, there could not be a little a, anything could happen, but I know for a fact that right here, it's a valid rule, whatever else happens. Cool. Any other questions? Yeah?
So let's say x goes to a and small e.
Yes. A, B, like that?
Yeah. And the follow of a contains b.
Yep.
Sorry, follow of x contains b.
Does it? Or are you asking me does it or would it?
And follow of a contains epsilon.
Let's say it's something and also epsilon. So what do I know? So what are you asking?
So, by writing the parser for x, so we'll first check whether whether t type contains b.
You're checking for, right? So you have a rule in the form of x goes to alpha, right? So you're checking the first of alpha. So you're checking the first of a, b, which in this case is going to be whatever this dot 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 is, and also b.
Yeah. So after that, we have to check for b again, the small b in the loop.
Yeah. So how would we write this? So let's see, we want to parse x. Right, so t type, get token. So I'm checking if t type is this, right? I'm going to do super and go like this, because I can. Right, so if t type is one of those things,
Parse A.
do I just want to call parse A though? Did this generate one of those terminals? Right, we first want to call unget token. Right, then we want to call parse A. So we think about the input string that's been generated here, right? So we were parsing something. The first thing is going to come from an A. We don't know. It's going to be a sequence of terminals. But the parse A function is going to handle that. Right? So when we first parse here, we read the first token. Maybe it came from here, maybe it came afterwards. We don't know, but we know it's included of first AB. Right? Then we call parse A, and when parse A returns, the parsing is now here. So now what do we know must have to be the next token here? B. It's got to be a B. So I do the same check I did above here. Right? And I have to check and consume that token because I call unget token here. Right? It could be the case, I don't know if it's 100% true, but it could be the case that parse B, that A could start with a B. Well, technically it can't, but whatever.
But what if parse A consumes the first token?
Good, it will. It'll consume whatever it needs to consume, right?
And but if A goes to epsilon, then it can consume the B.
But if you choose the rule A goes to epsilon, you don't consume any tokens. You would call unget token, right? So parse A is responsible for whatever it's doing. If it turns out that A went to epsilon, then the A part is nothing, right? And it would just be B. And so how would A know that it should go to epsilon?
Look in the follow set.
Yes, look in the follow set of A. So it would parse A would check for a token, and it would say, if I got a B, which is in the follow of A, then I know it must be the rule A goes to epsilon. And so it would call unget token, because that B did not come from A goes to epsilon, and then it would return to us. We would then get token and check that it's a little b, which you can't do. But just for clarification, right, that's what's going to happen here, which is the same sequence of steps that happens in here, right? We do the same thing. Cool. All right. Any other questions? A few more minutes. Yes.
Our predictive recursive descent parsers, they're only going to ever get and then maybe unget one token at a time?
Yes.
Just one. We'll never have to
Just
get 2 tokens in a row.
Never. Because then we're extra predictive, I guess. Predictive only by looking at one token ahead. Which feeds back into, if you want to figure out why, well, we've been only talking about first sets, it's only talking about the first token. Right? Could you write something that was the first 2 set that calculated the first 2 characters? Yes, you could do that. It would be a lot more complicated though.
But with the follow set aspect there, is it still sort of predictive recursive descent parsers use follow sets? I mean, obviously, but
How?
how?
Yes. So how do predictive recursive descent parsers use follow sets? When there's an epsilon, right? That's the key. When there's an epsilon in the first set, so if there was an epsilon in the first of, what rule do we have here? ACA, there's not. But if there's an epsilon in the first of ACA, we would also have to check for follow A to know if we chose this rule. So in the case of A goes to epsilon, or in the case of really A goes to anything, where epsilon exists in the first of that thing, right? How do we know if we choose A goes to alpha or A goes to beta, right? So we know because it's a predictive recursive descent parser that alpha and beta must be distinct, their first sets, right? That's rule 1, they have to be distinct. So if we're saying epsilon exists in the first of alpha, we know epsilon cannot exist in the first of beta.
As defined by the grammar. The grammar definition the production rules can't violate that rule.
Correct. Correct. If, assuming I've done my first and follow sets correctly and I've proven that it's a predictive recursive descent parser, which is why I'm trying to write a predictive recursive descent parser, then I know this for a fact. So now I can say, then if alpha went to nothing, this token that I'm reading came from after. It's the first token that came after that follows A, and so I would check. So your check for alpha, so if I'm checking the rule, like A goes to alpha, I would check if T-type in first of alpha, or T-type in follow of A. That's when I know this rule is chosen. Right? Alpha itself could just be the symbol epsilon, in which case we have the rule A goes to epsilon. But even if we know that the T-type is in follow of A, we still need to call, like let's say it's A goes to B and C, we'd still need to call parse C and parse B and then parse C so that they could deal with the fact that they, B and C, are going to epsilon. Because remember, we don't know exactly what this parser is going to do for each of these leaves in each of these cases. So we need to make sure we're calling the correct parsing functions to build this tree out. Like we don't want to short circuit it, because the tree, there does not exist a rule where A goes to epsilon, right? There's a rule that A has children B and C, and each of these maybe goes to epsilon, right? We want to figure out exactly what it is and what this tree looks like, because this is not a valid parse tree in this language. Yes?
So then in that case, we want to figure out where the epsilon position goes. We use the follow set of the.
We would use the follow of B, exactly. Yeah. These would each individually do it on their own. Call get token and figure out, oh, this is B goes to epsilon and choose that production rule.
And then if C epsilon, we do the same thing for
Yep.
follow C.
And you got to think, right? They're all reading the same token, but that's fine. Right? They're reading it and then they're putting it back to let somebody else deal with it. Right? Because A only cares about A goes to B, C. It doesn't care what B and C do. It just knows that it has to choose this rule A goes to B, C. Yeah.
So for my grammar, if I cannot write predictive recursive descent parser, then what option do I have?
Do it differently. So you either change your grammar to support a predictive recursive descent parser, which you can do, or you can essentially write a brute force parser that would basically, so in our parser, we stop anytime we get a syntax error. In a brute force parser, you would just try, you'd essentially first, if you had, let me go down front. If you had a rule like A goes to alpha and A goes to beta, right? You'd first basically say, try parse alpha, whatever, this is parsing all that stuff. And then if that failed, then try parsing a beta. And then if that fails, then there's actually a syntax error.
Easy to implement, but it would take longer, right?
Exactly, yes, because you have to try every possible, you're essentially trying all possible trees.
Will we have enough input on our project to tell the difference?
What?
Never mind.
Not sure how to answer that. Oh, you mean where it's like running forever or exponentially?
No, we have to implement this. Isn't it project 5, whatever you said we're going to have to build one of these?
You will be building, so you're going to be reading demos, the fact that the recording stops and an error happens, but it still saves the actual recording, that's like a good feature. Of course, if it didn't crash in the first place, that would be an even better feature, right? So yes, no, for project 5, you're going to be building, so there's a backend that takes in this intermediate language, which is in this graph, and runs and interprets the program, and you are doing the front part of that, which does the lexing, parsing, and generates this intermediate representation graph. So it's very similar to a parse tree. You're doing parsing, but instead of building an explicit parse tree, you're building this backend graph. Anyways, we can cross that bridge. Focus on project 3. Cool. All right, let's get back to semantics. Cool. All right, so we are now we've been looking at semantics, and we've been talking about names. So we've been talking about when I declare either a variable or a function in my program, how long is that declaration valid for, right? And we've seen that there's different types of these. There's different scopes, right? So C is basically, these would be global scope. X, bar, and foo are all names. They are declarations of names, and X is a variable with the type int. Bar is a function which returns nothing and takes in no parameters, 0 parameters. Foo is a function with the same signature, so it returns nothing and it accepts no parameters, but it also has a body defined. And inside here we have variable C, so we know that because C uses block level scoping, that this variable character C is going to be valid just within the block that it's defined, that it's declared. So it's going to be defined here till the end of this block. Whereas X, bar, and foo are all technically global, so their scope will exist from their declaration all the way to the end of the file and any other files that include them. Can talk to this variable, can use this variable. Cool, okay, so we kind of went through here. So what's the issue with this X here? So if we want to resolve this usage of the name X, right, we have an identifier X, how do we map this back to a declaration? How many X's are defined at this point?
The program or that block?
From this scope, how many X's could be accessible?
2,
3? 2? 3? 2? Just keep saying that.
2.
So walk me through. I can see how many X's, how many declarations of X's do I see in the program?
3.
3. So that's right. We're all clear on that? 3 declarations in the entire file. The first one's up at the top, global declaration. So we know this X is valid from here all the way to the end of the file. So could this be accessed here?
Yes.
Yes, that's one. The second one would be this X. Second declaration. What's the scope of this declaration? Just until the end of bar, right? We cannot refer to this X outside of this scope. So can we access that X from here?
No.
No. So then we have our third X declaration here, which is a character pointer called X, which is only accessible inside this inner block inside main. So is that accessible from here?
Yes.
Yes, so 2. We could only possibly access 2. So which one should be accessed? The closest one. Closest one, how?
Against the screen.
One you're really close with?
It's inside the same block.
Yeah, it's inside the same block, right? So we're going to look at how this actually happens, but we're going to look first at our local block, where X is. Is there an X declared inside this local block? If not, we look out into the block that contains that block. In this case, it's going to be here in main. This main block, does an X exist there? A declaration of X exists here?
No.
No, and then we check global. We check the global scope and we see that there is an X here. But our algorithm terminates on the first instance it finds of X. So it finds the X here in the local scope, it stops looking. So this is what language feature that you've learned about? What was that?
Variable shadowing.
Shadowing, variable shadowing, right? So this, when I call this variable here X, I'm now inside this block and all children blocks. I cannot refer to this global X at all. It shadows that global X. There's no way for me to say, I actually want the X that is the global X, not this local X. Right? Because we don't have any language features to talk about scope. It's just implicit there. Right? Yeah.
So what would happen if it was like, instead of a percent S, it was percent D, would it still refer to the char X and not the int X?
Yes. It would, what would it do? It would print out, because X is a character pointer, so inside X is a pointer, so there's an address inside X, and that address is where the string lives. So it would print out that address as an integer. So it would still probably work, unfortunately. This is why programming is hard. Yeah. Yes, it would print out this X as an integer, but not the global X. Yeah, sorry.
No. Does it not give you an error or a warning that X was already declared?
No. Because this, so, okay, I think we talked about that. You're supposed to think about that over the weekend, right?
Sorry.
Yeah, why doesn't it give you an error? X has already been declared.
Because curly braces are there.
Yeah, so the idea is, it really does, they're all kind of related. So coming back to shadowing, so because of the way the language is defined, this X declaration shadows the global X declaration. But if we tried to declare here in between int main, like another character pointer X, a global X, it would say, no, you can't do that. You've already declared a variable called X in the same scope. So in one scope, we can only have one declaration of the same name. Because the idea is, anytime we use an X, we have to know, or a name, we need to know exactly what declaration I'm referring to. So here, because of the way we resolve it, there's no ambiguity. We check our local scope, there's one X, done. But if there were two global X's, I would not know which one necessarily I was talking about. Cool.
So
Yes.
you're saying we can't put X equals 10 inside that scope?
Inside where? Here?
Yeah.
No, you could. So this is not a declaration. This is using the variable X.
Okay.
Right? Declarations are declaring X. Like here, I'm declaring there is a variable called X, which has the type int. So languages are different in how they do this. Specifically in C, you have to explicitly declare a variable. And for those of you who've experimented with just coding C, you actually have to declare them at the beginning of every block. You can't declare it later on. But yes.
But I think the question was that because the char pointer is shadowing the global, if you put another x equals 10 below your last printf statement,
Yes.
would it set the char pointer to 10,
Yes.
possibly puke because it's a null pointer because the 10 memory address isn't accessible? Or is it going to, is that what would happen?
Yes. So if you move this x equals 10 line here, it would still work and compile. It would probably give you maybe a type warning. But yeah, you can set a character pointer to an explicit value, and that's, you're saying instead of my character string starting at whatever memory address is inside the variable x, it's actually at memory location 10. Which when you try to access that would probably fail because memory address 10 is not allocated to your program. Yes. Sorry, just a second. That's a segmentation fault. Because that segment of memory, which contains memory address 10, is not allocated to your program, so it's a segmentation fault. That's where segmentation faults are. Yes, that's exactly what it means. Sorry, there's over here first. Yeah.
So you were saying that in C, the variables have to be declared at the top of the scope, is that right?
Yes.
Is that true for C99 as well?
I don't know.
Okay, because I know that you can do it, but I'm wondering now if it does like JavaScript where it does hoisting or something like that.
It may.
Because I'm wondering, what if you move the x equals 10 down 2 lines from where it is, so just above the char star x.
Like here?
No, down in the main.
Oh, this?
And what if you moved it just inside of the scope, but at the top?
Good question. Now we get to experiment. I didn't plan on doing this, but this is fun. Temp, what are we doing? Okay. So we have our program here. The first thing we should do is make sure this, make it a little bigger for you. The first thing we should do is make sure this compiles, right? Before we actually like. Nope, it's not actually a thing. What? Oh, have to actually write out your file. There we go. Okay, so it's giving me one warning that this integer x is unused, right? Which is kind of nice. Okay, so we have, so just to make it super clear, if we had like a character pointer x, right, it should give me an error. So I'm trying to redefine x with a different type. Ooh, interesting. Could I actually call it an int?
It's because it's not completely defined when it's up there in x. It's been declared, but it's like a weird form of declaration.
Whoa, crazy.
It's like pseudo.
Oh, yeah. Okay, so it's the same thing as the function, right? So we're declaring that there is a variable x. Just like here, we're declaring there is a function bar, but we don't have a body for bar yet. That is super weird. I did not know you could do that. See? Learn something new. It's good that we experimented. Okay. So the other thing we wanted to try is what if we did this? Huh. Okay, but this is also not the GCC compiler. This is a Clang, so it's different.
Didn't you do it in GCC?
I did GCC, but on the Mac, GCC is linked to Clang. There's no GCC because they switched everything over to Clang. So now the interesting thing is, what happens if I print out X? That is crazy. Let's verify that this works really quickly. Okay, so this actually does, the warning tells you it still compiles, but it does, Clang is doing some advanced, like looking at this string that you're using for the format string and trying to determine. And if I ran it, yeah, instead of testing, I see this super large value, right? Okay, so that's cool. Let's see if this actually works in GCC. Fortunately, I'm going to use, where am I at? Okay. I think I'm here. What do we call this file? Okay, cool. By that, so if I GCC. Huh. That is weird. What if there's a way I can make it be the old standard? Oh.
I have to say, say I'm shocked that C doesn't prevent you from shooting yourself in the foot.
Is that sarcasm? That's basically all C does is helps you shoot yourself in the foot. And C++, it's just more advanced ways of shooting yourself in the foot. Oh, just, see, this is silly. This is not standard, all right.
Single.
Yeah, you're not supposed to be it.
I think you need C89.
Huh. It's crazy. I was doing this with somebody, weren't we playing with this and it didn't work?
Wasn't it just giving warnings? Didn't they compile them?
Yeah, I did give warnings, it did compile. Alright, I don't know how to prove that that was a thing. Maybe there's an older standard, yeah.
Maybe it's saying something about a non-void function. Maybe it's because you're not returning something in main.
Could be. Well, that would be one thing. Return. Still only this unused variable. ANSI C? Yeah, I thought. Huh. Alright, well, we're gonna have to get up on this, but. Okay, maybe it's because we have this global X. Just want to see this error. Mainly to know I'm not crazy.
You are using x is equal to 10.
Oh, because I'm printing out X here. I see. Any other? But I want, how do I make it? Still only warnings. All right, well, turns out I don't know anything. Cool. Computers, how do they work?
Remove the curly braces in the main.
Remove what?
This thing.
Remove braces?
Yeah.
That's going to
No,
completely
no,
break
no.
it. This?
Before character start.
What?
Or the inside.
Inside.
Yeah, I shouldn't be able to use this X here. I don't know. Maybe it's just in for loops, because I know you can't declare variables inside of a for loop. Because that's what we looked at. Right?
Yeah, all the things.
Yeah, you definitely can't do, okay.
No, you can't do that. They should be.
In C you can.
But I thought that was because you're supposed to declare it.
It was there until you definitely can't do that.
Hey, there we got it. Error. Redeclaration of X with no linkage. For loop, initial declarations are only allowed in C99. Okay, that's definitely true. Cool. All right, let's go back. Any other experiments we want to run? Cool. Okay. So part of what we want to do here is we always want to understand what we're looking at here. We're specifically looking at static scoping, right? We're saying that no matter how this program executes, this instance of X here is going to refer to this declaration of X. And we know that because for every declaration we can calculate based on the scoping rules of our language, we can say that X is valid here all the way to the end of the program. Just like bar is valid from there all the way to the end of the program. And that's why we can call bar here in foo without there being a body for bar. Right? Because the compiler knows, okay, you want to call this function called bar, you told me about it, and you know that later you're going to tell me exactly what bar is, but for now I can know that you just want to call the function bar. Okay, same with foo. Then we have a character C that's only valid in this block. Right? And think about it. Think about how weird it would be if in another function we could refer to this value C. like in Baz, if we could say, hey, print out the value of C from foo, right? That doesn't even make sense, right? Because what if C is changed? What if foo is never executed, right? Yes?
Well, it kind of does if you think abstractly enough that all methods and functions are classes, and all classes are just methods and functions. And so that C is a member of a class called foo, which is really a method. And so you're accessing a member. So you just restructure your brain if you want to do stuff like that. But it's not available.
The key problem is that C depends and changes on each it's a new instance of C for every invocation of the function foo. So it'd be like you creating a new object with a new method foo, which had a new class C or a member C. So yeah, it'd be like, which one are you referring to? Because you already executed foo twice. So which C do you actually want to access? Yeah.
From bar where it calls Baz.
Yes.
So bar has its own block, and then when it calls Baz, is Baz inside that block?
Say that again?
When bar
Yes.
calls Baz.
Bar calls Baz. Boom. Here.
Right. Is that X going to be X100 when it calls it that? That new global value?
So what is this X here when we're looking at it statically? The global X. Yes. So for static scoping, which is the way we're used to, this X is only going to refer to this X here. Every single execution, no matter what functions we call before or after. We'll see dynamic scoping does exactly what you're talking about. It actually looks up the call chain to see where was the last X declared, and it uses that X. Cool.
If you pass in the X though, it'd be 100, right?
If I did what?
If you pass the X in to Baz from bar, it would be 100, right?
Yes, if you passed in as a parameter to Baz the value X, it would be 100. Because inside this scope here, X is exactly 100. This X. But there are no uses of X, which is why I complained with the warning. Cool. And so I didn't draw any of the functions, but they're the same. Oh no, bar is still declared here, cool. So we have int X, so int X, right, is valid only within this scope, this int X. And similarly, this character pointer X is valid only within this block, because this is the scoping rules of C. Okay, so we're doing this statically, right? We do it once, we map the variable usages to the declarations, and that way we can see what happens when variables change. So, I want to get, okay, yeah, cool. So as the program goes, we're mapping, right? We already did this. We mapped bar to this declaration of bar, which is here, right? We mapped this X to this global X, right? Because we said, is there an X defined in this local scope? No. So then we need to access the global X. And the same with C. We say, is there a C in the local scope?
Yes.
Yes, so that is the C that this usage of C refers to. Cool. The printf, where'd it come from?
Include.
Yeah, it came from the include, right? It's not magic. If you go look at standard.io.h, it's going to have a function that looks exactly, well, very similar to this bar declaration that says there's a function called printf. Here are the parameters, and here's the return value. Cool. This X refers to the global X, right? It looks in its local scope. There's no variable named X declared there, so it checks the global scope. Cool, and so on and so forth, right? This X, does this refer to this X over here? No, it doesn't make sense, right? A, we talked about it. And B, it checks its local scope. Doesn't X exist in this local scope? No. And it doesn't, we can't check this child scope, right? This scope hasn't happened yet, right? We can't check that, so it has to be the global X that this X maps to. And this X, as we saw, is the local X. So, we actually saw this. If we compile this, it'll compile. It will, depending on the compiler, it'll give a warning about not having a return in main. And then when we run it, it's going to output testing first, right? So that's another thing we need to be able to do. This is a skill that you're going to have throughout this class, is be able to look at C code and tell me what the output is going to be when you execute this code, right? So this means you need to be able to step through and think about exactly what's going to happen, right? So Main's going to be executed first. So what's the first thing that's going to happen?
The assignment.
The assignment. So which x is going to be set to 10?
The global x.
Global x. So global x is going to get the value 10. Then we get into this block. We initialize a local x in this block to be the character string testing. And so when we print out, what are we going to print out?
Testing.
Testing as a string. So we just print out testing. So now we're going to call foo, right? So we're going to call foo. We're going to set this character c to be the character c. And then we call bar. And bar sets which x to be 100?
That local x.
The local x. And then we call baz, and baz prints out x.
10.
10. So it should be what? The global x, which has the value 10. Okay. And then which x is this assignment happening to? The global x, right. It's going to be 1,333. Oh. And then it's going to come back from bar. So baz returns, which comes here. Bar returns, which comes here. And then it's printing out x space c. So this x is the global x, which has the value 337, and the character c. So it's going to print out 1337 space c. Foo returns, and then we're done. That's it. Cool. Okay, so this is static scoping. This is something that we are very familiar with because this is how we write most programs in our programming language. An alternative design decision from the language designer's perspective, right? They're the ones who decide the semantics of this language, so they choose which type of scoping semantics do I want to use. So instead of static scoping, you can actually have dynamic scoping. And the idea is the symbol table, where the symbol table maps declarations, names to declarations, it's created and updated as the program executes at runtime. So as the program is executing, as new blocks and new scopes are being entered, the symbol table is being dynamically created. And so when we want to resolve a name called X, we look it up in the table for the last encounter of declaration X. Whereas on static scoping, we can do that beforehand, right? We look first in the local scope, and then we look in the parent scope, and then the parent scope, and then finally the global scope. And if we don't find it, then we say that you're using a variable that hasn't been declared, right? But that's statically. We're looking at the program itself and the code in the program. The lookup tree and the lookup that we're going to perform depends on the actual execution of the program. So we'll see how that affects things. So X could actually completely change. It could be sometimes an integer, it could be sometimes a string, it could be a function, depending on which path we take through the program. So just so you realize this isn't just some crazy esoteric feature, Common Lisp as a language actually allows both. So it does static scoping, but you can specifically declare variables to say, I want these variables done dynamically. And we'll talk about, once we understand how it works, we'll talk about kind of why it does it that way. Okay, so here's our fancy program that we already looked at. And so what we're going to go through is we're basically going to step through the program as if we're executing it, and we're going to build the symbol table for all the scopes as we execute it. So the first scope is which scope? The global scope, right? You can think about, we're not executing foo, right? Foo is not the first function that's executed, but we are looking at all the declarations, right? So we look and we see, aha, in the global scope, there's a name called X, and it happens to be an integer, right? You can't really see it now, you'll see it later, but this is a table with 3 columns. The first one's the name, the second one is just the type information, the metadata, and the right one is the value, the actual value that that variable holds. So then here we look at bar, and we say, okay, bar is a function. It takes in nothing and returns nothing. but it doesn't have a body. We don't know where the body of bar is yet, which is just a declaration of bar. We see foo, and we see foo. We see that it's the same. It's the same function signature. It returns nothing and takes in nothing. But it's actually, body is declared on line 4. We see baz, we make a similar thing. Then when we see bar, do we create a new name in our symbol table called bar?
No.
No, we look it up and we see, did we see bar? Yes. We've seen bar. This is the body of bar. So we'd update the body of bar to say bar is actually defined on line 13. And then I do the same thing, right? Main is just a function just like every other function. And so main, we're saying main is a function that takes in nothing and returns an integer, which we didn't show here. And it's defined on line 17. So is that everything in my global scope? Cool. So now that I go through and build up this global scope, which function gets executed first? Main, right? That's the semantics of C. Main is the function that gets executed first. So now here, when we're executing this line of code, we say, okay, what do we need? We need to resolve x to some declaration, right? So we look it up in our symbol tree. We'll see we start at the bottom with the leastmost symbol. You can see we're going to push things on and we're going to pop things off. But we look up and we see, do we see an x in this symbol table?
Yes.
Yeah. So let's set the value of that x to be 10. Right? Happens to be the global scope. Cool. We enter a new scope here. And now when we enter a new scope, I'm going to kind of draw it with like an arrow and then a new box. Right? Because we've entered this new scope dynamically. And then as we see declarations, we're going to say, hey, there's a new variable named x, and its type is a character pointer, and it has the string testing in it, which technically isn't true, it's pointing to the string testing, but we'll get to the semantics of pointers later. So now when I see this x, do I say, oh, this x is the same thing as this global x? No, right? I look up in my symbol table, basically starting from the bottom and looking up and saying, is there an x in this symbol table? Yes, there's an x character pointer. So this is what this x refers to. So when I print out, I'm going to print out the value testing. Has anything changed so far? No, it's been the same. Now what happens once I leave this scope? Yeah, I want to remove all variables that were declared in that scope. Right? So for my symbol table, I want to pop off all of these variables and get rid of everything here. So I just get rid of it, right? It's done. Now I call the function foo, so I'm going to jump into foo. And did I enter a new scope? Yes. Yeah, so I need to add another arrow and another scope here. And now I see here I'm declaring a new character C with the value C. Then I call bar, and I'm in bar. Did I enter a new scope?
Yes.
Yes. Did I get rid of foo's scope? No. Right? And can you see that the symbol table is mimicking the current call chain? Right? We have the global variables, which called main. Right? But main didn't declare anything, so we don't have main in our symbol table. And then main called foo, and foo declared C. And then C is going to include C then called bar, and bar now includes a new integer x that's declared in bar. Yeah.
When it looks up this trace, does it check the typing? So if you set, I don't know, so at some point there, if you set x to a string, would it look up and say, well, there's an x in this scope, but it's not a character pointer, so we're going to keep going up in scope until we find an x that matches the type of what we're trying to do? Does it operate that way?
Short answer, not usually.
Okay.
We'll actually see. Normally, no. So it will do type checking. So if it's expecting a string, but you actually gave it something else, like an integer, usually it'll do type checking right then, like Python does type checking then. Otherwise, it's not going to do it, and you'll have to kind of manually, or it will either throw an exception at that specific point, but it won't try to find the correct type. Because it doesn't know that X, here it just sees an instance of X and is trying to look it up. It doesn't know what type X is. It may be able to infer that from the context, which we'll look at ways that you can actually do that. But without that, then no, you can't know exactly which X you're trying to talk about. Cool, what's our time? Oh, we're over. Okay, cool.